Hey everyone, thank you for checking out our screencast today on function transformations. In this section, we're going to examine how a graph of a function can be transformed by shifting or translating, stretching or compressing, or reflecting. So let's take a look at our first function here. We have the absolute value of x, and then we have the absolute value of x plus 3, and the absolute value of x minus 4. So what will adding or subtracting a number outside the absolute value do to a graph? So we call that a plus k. What that's going to do is that's going to vertically shift or translate. The actual mathematical word is translate, but we usually say shift, up or down. So we call it a vertical shift. And if k is positive, it's up. And if k is negative, it's down. Now what if we add or subtract inside of the function, right? So we have here an example of x squared, and x plus 3 squared, and x minus 2 squared. So this time you can see that the x squared function, the original x squared function here, is being moved left or right. Okay, so this one is called a horizontal shift, or a horizontal translation, left or right. But this time it's actually the opposite of the number. So if it's plus 3, so we call this h here, this number that we're adding inside the function. If h is positive, we actually move it to the left. And if h is negative, we'll move to the right. Okay, so if it's, well, I shouldn't say h is negative, h is positive. I should say this. Let's change that to, if it's x plus h, it moves left. And if it's x minus h, it'll move to the right. The third one here, if we multiply the function by some number, so you see the x squared function in black, and if we multiply by a number bigger than 1, you see what happens in green, and a number smaller than 1, you see what happens in blue. Okay, this is called a vertical stretch or vertical compression. So vertical stretch or vertical compression. It's a vertical stretch if that a number is bigger than 1. And if it's a vertical compression, if the absolute value of a is less than 1. Okay, we say absolute value of a because if it's negative 4, it's going to be a stretch. If it's negative 1,000, it's going to be a stretch. Only if it's a number that's between 0 and 1, absolute value between 0 and 1 would be a compression. Okay? And what we would do then is we multiply each y by that number a to stretch it or compress it. Fourth one, if we have a multiplication inside the function, so you can kind of see what that looks like here. The black one's the original absolute value. The green one, if you multiply by 2, and then the blue one, if you multiply by 1/3. This is going to be a horizontal stretch or compression. Okay, and it's actually the opposite here. The stretch is going to be the absolute value of b is less than 1, and the compression will be the absolute value of b is greater than 1. Okay, we actually stretch it or compress it not by multiplying by b here, but by dividing it by b, so x over b. Whereas up here, it was ay, so x over b. Fifth one, the following functions have been graphed below. We have the absolute value of x and the root x, and you can see what happens if we multiply outside the function by a negative sign. Okay, this is going to be called a vertical reflection, or in other words, a reflection about the y-axis. So we put about the x-axis, about the x-axis. So we flip it over the x-axis. The other word for reflect would be a flip. Sometimes we just call it a flip, but the mathematical word we use is reflect. And the last one, what if we had a negative inside the function like we have here? So negative inside the function, this is called a horizontal reflection. And that's about the y-axis. Okay, so summarizing, this is what our graph could look like here. All right, it's important to know inside a function that we have to factor out that b. Basically, the number in front of x we want to be 1. So if it's not 1, we need to factor that out to see the horizontal shift properly. So a, let's remember, is a vertical shift. Sorry, vertical stretch or compression. Sorry about that. I was doing them in the order we did them earlier today. Vertical stretch or compression, depending on the number in front of the function. B is a horizontal stretch or compression. K is our vertical, save some time here, our vertical shift, and H is our horizontal shift. Okay? And don't forget the negatives out in front could do our reflections as well. The order to apply these, yes, there is an actual order you got to apply them. You can't just do whatever you want in any order. The order to apply these to our original XY pairs would be first, all of our horizontal things. So first it would be H, and then it would be plus or minus B, and then our vertical things. So then it would be A, and then plus or minus K. I guess I should put plus or minus in front of all of them, right? But you get the picture. So HBAK. Shift, horizontal shift first, horizontal stretch or shrink second, along with whether or not that would be flipped. And then the vertical stretch or shrink, and then the vertical shift at the end. All right, so let's take a look now at some problems and some transformations and in what order we should be applying them to our graphs. So number 6, we see that there are 2 transformations taking place here. The negative out in front, multiplying the function, and the plus 7 inside the parentheses. So we are to start with doing the horizontal shift left 7. So we're just going to write shift or translation left 7. And you don't got to tell me horizontal if you're going to say left and right. That's fine. And then the negative out in front is going to reflect it vertically. So you can say vertical reflection, or you can say reflection over x-axis. Number 7, again, we see 2 transformations, the minus 10 and the minus 20. So first we would do the shift right 10, and then the shift down 20. Remember that for the vertical shifts, we go the same way the sign is telling us to go. But for horizontal, we go the opposite way. Number 8, we see 2 more transformations. The first thing we would do is we would stretch vertically. So I would say a vertical stretch by a factor of 4. And then the 17 after that, we would shift up 17. This final one's tricky here. We have this equation. The first thing we actually need to do is to factor out a 2 like so. There's actually 4 transformations taking place here. 1, 2, 3, 4. So the order for these is going to be, first we're going to shift left 2.5 or 5 halves. And then we're going to stretch or compress, however we want to say that here, by horizontally by a factor of 1/2. Remember, it's going to be x over b, so x over 2. And then we're going to stretch vertically, by a factor of 1/3. And then finally, we're going to shift down 1. All right, so let's try some problems here. We have this weird looking function over here that kind of looks like 2 line segments in a semicircle. Consider the function f of x whose graph is below. Apply the given transformations to the function at the right. Use a different color for each graph, and be sure to write the rule and complete the table. Then compare your results with other students. All right, so we have this graph here, and we have 2 transformations being taken place here. One is going to be a shift left 2 and a shift down 5. So f of x plus 2 minus 5. The first point is going to move to -11, -5, and then -8, -7, -2, -5, 1, -1, and then 4, -5. So if we plot those points here, let's see, -11, -5, right about here, -8, -7, let's go a little further than that. This is 8 here, so -11 be over here. There's -11, -5. -8, -7. -2, -5. 1, -1. And 4, -5. So our graph might look like that. Okay, part B. So now we're going to shift left 1 and down 3. So our points are going to be -10, -3, -7, -5, -1, -3, 2, 1, and 5, -3. All right, something we forgot to do for the last one is to write the rule here. The rule is essentially, if we were to those vectors, right, x comma y would go to x minus 1, y minus 3. All right, plot our points here. So -10, -3 would be here. -7, -5, -1, -3, 2, 1, and 5, -3. And our graph should look something like this. Let's go back to A. We forgot to write the rule for this one. So xy would go to x minus 2, y minus 5. All right, C. So our rule here is going to be xy is going to go to, so we're going to move the x's to the right 3. So it's going to be x plus 3. And then we're going to multiply the y's by -2. So it'll be -2y. All right, so our points are going to be -6, 0. -3, 4. 3, 0. 6, -8. and 9, 0. So if we plot these, 6, 0, negative 3, 4, 3, 0, 6, negative 8, and 9, 0. So it should look like this. So the last one here. F of 3 halves x plus 2. So our rule, xy, is going to go to, for the y coordinates, we're just going to add 2. That's pretty simple. With the x coordinates, remember, we're going to divide by that number, so we're actually going to multiply by 2/3. So it's 2/3 x, 2/3 x, y plus 2. So our points will be negative 6, 2, negative 4, 0, 0, 2, 2, 6, 4, 2. So negative 6, 2, negative 4, 0, 0, 2, 2, 6, and 4, 2. And there we have it. You can see that it is horizontally compressed a little bit and moved up 2. That will do it for our lesson today on transformations. Hope to see you again soon.